Uh, Good morning, everyone. Thank you for joining us. We are Team Lunar ROADSTER, and we'll be presenting our fall validation demonstration. So, starting off, we have with us in the team Ankit, we have Bashwant and Simpson at the operations terminal, William managing all the logistics of the presentation today, and myself, Deepam. So, as we all know, that humans are returning to the moon. With the upcoming Artemis missions planned near the poles of the moon, specifically the south pole of the moon, the regions around the pole, which are shown here in yellow, will become a high density sites of interest. There will be a lot of interest points near the pole that will facilitate polar exploration and in the future, maybe even colonization of the moon. Wouldn't it be better to have a perpetual motion, having a machine that will perpetually go around this route? But the question is it possible for a solar powered rover to repeatedly drive around the moon and never encounter a sunset? It turns out it is. We call that sun synchronous circumnavigation. The need for that is evident because of the small scale of the moon and with having no atmosphere up there, the intensity of solar energy is pretty high that can be tapped into and be used for such kind of a perpetual motion machine. We did the math and found that at higher latitudes of 75 or 80 degrees, we just need to go at, say, a jogging speed of 3 to 4 kilometers per hour. But that's only possible if the path is flat, circular, and traversable. Right now, it's not. And that's where our project comes in, the Lunar ROADSTER. It's an autonomous moon-working rover capable of finding ideal exploration routes and creating traversable surface trains. The primary use case is as follows. We get a map from a previous orbiter. We select a reference latitude. The existing current original traversable path would look somewhat like this. You can see that it's windy and it goes around a bunch of craters, trying to avoid them. That increases the time it takes to go around this latitude, and hence we might lose the sun synchronous idea of it. That's where our rover comes in, the Lunar ROADSTER. It will select the craters it needs to groom and target. It can also select the craters it needs to avoid because of size or other reasons. And it will carry out the terrain manipulation along this route while filling up the craters in the way, thereby making the path more circular and hugging the reference latitude that we selected earlier. While we start and prep with the demonstration, I'll go over some highlights of the rover. Starting off, it has a 60-centimeter dozer blade, as you see in the front, with a high tool actuation. That makes it 3 times better and stronger from its predecessor. The custom wheels have very high rim pull and maximized grip, and paired with high torque drive motors, it gives a superior pushing power to us. The reliable circuitry and the efficient power distribution system that we designed custom for our use case makes it an optimal and specialized machine for crater grooming. Let's look at the demonstration.
So moving on to today's demonstration is divided into, our mission statement is that the Roadster will use its excavator to groom craters and create a traversable circuitous path around the moon yard. The procedure is as follows. Before you guys got here, we did some pre-demo setup. This involved preparing the test environment, which are the craters that you see here. There are currently 4 craters in the moon yard. We obtained a global map using our laser scanner. We then converted this to a 2D cost map. The idea is to emulate the data that we would get from the LRO, or the Lunar Reconnaissance Orbiter. Further, we set up our total station, we calibrated our localizations, we set up this GUI to monitor the mission, and we set up the operations terminal where Bashwant and Simpson will be monitoring the mission from. Further, when the demo starts, we send a start mission command. The rover will traverse to its target crater. It will perceive the crater, identify how it will want to manipulate the crater, and manipulate the crater. After this is done, it will validate how well it has done this, and if it needs a second pass. If it succeeds, it will move on to the next crater until all craters are finished, and then the mission will stop. So while the rover has currently, I would want you to come towards the moon yard now so you can see what's going on. So the rover has traversed to the crater now. It is currently in the perception state. What it's trying to do is identify the centroid of the crater where it lies in the world frame, as well as the diameter. Using this, it will plan some poses that will allow it to manipulate. We do this via a custom YOLO V8 model. We trained this on a custom data set that we collected in the moon yard. After this, in the manipulation, what is going to happen is we generate these 4 poses. Our manipulation is divided into 2 passes, forward grading and backward grading. which should start anytime now. So now currently it's at what we call the source position. That's when the tool goes down. It's going to go to about half of the crater to perform the forward grading function. This is our forward grading function. After this, the tool will go back up and it will move towards the source backblade. Backblading is where we will use the back of the blade to completely groom the crater. This method of manipulation, we're using this so that we only have to attack the crater in one direction and we don't have to go to multiple directions to fill in the complete crater. So now the backward pass will happen and you will see that it will almost completely grade the crater. So while this is happening, after when this is done, we'll move on to the validation subsystem. So our metric for calling a crater groomed is that the maximum gradient around that area should be 5 degrees. So if you look at flat terrain, the gradient would be about 2 degrees. But if there was a crater like the others that you see there, the maximum gradient would be 15, 10, something like that. So that's how we're validating or calling our crater groomed. So we get a point cloud from the Z camera, and we voxel down sample and estimate normals with respect to the y-axis. And when those normals are estimated, we'll be able to figure out whether or not it is within 5 degrees. If it is within 5 degrees, which it was in this case, it's going to move on to the next crater. Hopefully, one of these craters doesn't do as well as it just did, so that you'll be able to see the validation subsystem in action. So while it traverses to the next crater, I'd like to tell you how the rover localizes itself. So there are 3 things on the Roadster that are being used for localization. One is the Leica total station, which is tracking the rover. There is an onboard IMU as well as wheel encoders. So using all 3 of these, we get a global localization. And then using just the IMU and the wheel encoders, we get a local localization. By fusing these into an extended Kalman filter, we get a very continuous rover pose. So now it has reached the second crater, it'll go through the same pipeline again of perceiving and manipulating. While it does so, I'd like to tell you about our custom navigation planner. So as we mentioned before, that the navigation planner gets a LRO input, that is the 2D cost map. But we didn't want to solely rely on the 2D cost map, which is why in the map that you see here, there are 5 craters, but in the Moonyard, there are only 4. So what we're trying to emulate is that this crater is a false positive given to us by the LRO. That means when the rover traverses to this crater, which is supposed to be somewhere in that area, it should not manipulate. It should realize that it does not need to manipulate and move to the next crater directly. So we're not only relying on this 2D cost map. The global nav planner creates, so it optimizes certain cost functions. The first one is based on this latitude. That is our reference latitude. The main point of sun synchronous navigation is that we want to hug a latitude, and this is our first cost function. The other is that we want to reach all of the craters that we plan to groom. And using this, we get this reference ring. So this reference ring is our main reference for the global nav planner. After this, the global nav planner will try to hug this ring as much as possible while it goes throughout its motion. So this planner is a lattice A star with Ackermann primitives. What that means is in a normal A star, it might generate some huge turns that our rover will not be able to do because we only have Ackermann steering. So we added those primitives so that the paths that are generated are actually executable by the rover. And our navigation controller is a normal pure pursuit controller. So the pipeline is we get the 2D cost map, it's sent to the navigation planner, which generates waypoints, which sends it to the navigation controller, and the controller itself sends actuator commands to the actuators. So sometimes what happens is because we have a heavy cost on penalizing backward motion, during manipulation, the global nav planner tries to plan paths which are outside, trying to hug back into the latitude. That is what you see here. We don't use these paths because the manipulation controller is running, but it does show up on the GUI. So now I think we're going to the second pass depending on how the validation went. So if we're going to the second pass, you'll see the same. We're going to the next crater. Okay, so I guess validation succeeded. So to show that validation does work, we'll go to the place where there is no crater, and we'll be able to see that the validation functions. Moving on to the, moving on. So now that I've explained all subsystems, it'll be easier to follow what our FSM system works like. So we basically, when we send the start mission, it is sent to our global nav planner. The global nav planner plans the waypoints that it needs to complete the entire mission and sends it one by one to the global nav controller. The global nav controller generates the actuator commands that sends the rover to the crater. And once we reach the crater, the first thing we do is run validation. If there is a crater, validation is always going to fail. If validation fails, we move on to the perception subsystem, where we generate the manipulation plan. After the manipulation plan is generated, we will do the manipulation. And once manipulation planner outputs success, we will go back to validation. If validation then outputs failure again, we go to second pass. Otherwise, we go back to the global nav controller, moving on to the next crater. Once all craters are complete, the rover will send a no goals remaining signal and the mission will be stopped. So currently, it's at the crater where it's at the place where there's supposed to be a crater, but there is currently no crater. So ideally, what should happen is it should just move on to the next crater. So while the mission is completed, we'll be open to some questions. We'll be showing you some results that we've got over many test runs when the mission is complete. So please ask us any questions that you have.
Did it avoid the crater on the side?
Yeah, it did. So the reference plan that we create is supposed to avoid that. Otherwise, since there's a circular reference latitude, it would have gone into the crater itself.
So it measured its diameter.
Not that one,
Not
because
that one.
because that is a thing we got from the LRO that we already knew it's too big. Yeah.
Validation on this one then and decide that.
Yeah. So our first thing it does is validation. So if validation fails, is only when perception starts. If this output success, we're just going to go back to global nav planner. Any other questions, please? Anything?
Yeah, when you are forced to do it a second time, what's the most common reason?
The most common reason is the tool height is not low enough. So in our second pass, we always lower the tool height so that we're able to get a better finish onto the ground surface. But if we lower the tool height too much in the first pass itself, it's going to start pushing too much sand and then it starts digging into the ground. So that's like a balance that we had to strike with multiple passes or just a single pass.
Why is the localization unstable?
The localization is unstable. Okay. Sorry?
What was the question?
The question was, why is the localization unstable?
Okay, the localization is unstable due to basically latency. The total station data is not continuous. It's published at a rate, like at a discrete rate, which is actually why we moved to the SkyCam, which is our next demonstration in FPD Encore, where we will be removing the total station entirely and using the lights on the ceiling to localize the rover. That is our improvement for next week, and that is the need for that. That the localization is sometimes it drifts based on, because it's an EKF, sometimes the odometry drifts and the total station is supposed to correct it, but it's not able to correct it always. That's why we're moving to a better method of localization, which is also actually more lunar accurate, because obviously you don't have a total station on the moon.
Some people down here don't know what onshore means. Just means come back next week.
A cooler demonstration, yeah.
Also, the total station publishes all the position data through another computer. So that adds on, and it's done over Wi-Fi connection. So that adds on to the latency.
Do you have a success criterion on what percentage of the crater you cover?
No, it's the 5% gradient. If there's a 5% gradient, it's gonna try again until it gets somewhere near to that. Yeah. So like the dip that you see in the middle, it may or may not be 5 degrees. If it is above 5 degrees, it's going to try again. But if it's not, it's just going to end the mission. And once the mission ends, what we're going to do is just run the rover in a circular path to show that this path is now traversable while we demonstrate the results.
Right.
On this one, on the right-hand side, which didn't quite get through because it moved a little bit off center through the crater.
Yeah.
That looks like it's maybe more than 5%, but is it going to ignore that? Because it's far enough outside of the potential path?
It may or may not. Like it's depending on how much it's captured in the point cloud. Even if it does not, it's going to drive over it, so it's going to flatten it out.
Yeah. And the validation system is designed in such a way that it averages out. So if there's like just one berm in the site, it might not like add that much to the
Average, yeah.
Region.
Yes, yeah. So
I'm sorry.
Mhm.
But I guess we decided that very short.
Yes. So the huge point cloud that we get from the Z camera, we reduce the size. Especially, it's possible that because it has such a big field of view, it might capture certain regions which are like obstacles or certain things like that. So we don't want to add that in our gradient calculation. So in order to do that, we crop the region we look at, and it's localized to where the crater is.
It's about a 1 meter by 1 meter region in front of the rover, but there are some blind spots. For example, where the tool is itself, if there's a berm that ends up behind the tool, we're not able to capture that. So there are some improvements that we would like to make to the system, but yeah, that is what it is. So now, since the mission is complete, I'd like to direct you back towards the screen over here so we can showcase some results.
All right. So before today, obviously throughout the semester and especially in the past few weeks, we ran a bunch of tests and validated some of the results and requirements that we have set in the presentations before. So starting off, the Roadster plans a path with a cumulative deviation of up to 25% from the chosen latitudes. Then, so the reference latitude that we choose in the beginning, we make sure that the planned path that we see on the GUI is less than 25% deviated from the reference latitude. This deviation usually occurs because it might the 2D cost map might show that there are some big craters that it needs to go around, and it can't hug the reference latitude that much, or there are some other obstacles that it needs to go around. So the reference radius that we have for this moonyard is around 2.3 meters, which amounts to the latitude length of 14.6 meters. Out of a bunch of tests, we figured out that the least deviation is about 21.47%. The maximum we found was 24.3, but the average was well below the 25% limit, which was 22.89. So that satisfied our requirement. Similarly, there's another metric where it follows a planned path to a maximum deviation of 10%. This deviation usually occurs because of localization or navigation errors that we also saw during the demonstration. So again, we did a bunch of tests, and the least deviation we found was in one of our best runs, which was 0.09%. The max was 12.98%, and the mean was 7%, which is again well below our 10% limit. We also calculated the contact pressure of our Roadster. We weighed the rover, it comes out to less than 24 kgs. And based on the contact area of the wheels, we found that the contact pressure for the moon region is 1.37 kilopascals. We did a similar analysis on different planetary objects like Earth, Moon, Mars, and did a study of how much the contact pressure changes. And we also have a study here where it shows that in low contact pressures, we get lower sinkage, which is better for our application. As demonstrated in the presentation, we avoid the craters which are ungradable, and that is given by the metric of greater than or equal to 0.5 meters. So that big crater in the far off corner that we see is more than the metric, and that is why it selects that as an ungradable crater, and the rest are selected as a gradable one. That's how we get the rough coordinates in the world frame for the gradable craters. So yeah, similarly, 0.5 meters is the maximum that we usually target. All the craters that we saw today are within that 0.5 meters limit. So we are able to successfully grade them, and they all have a depth up to 0.1 meters. So let's look at some requirements that we've satisfied so far.
So moving on to our functional requirements, based on all the requirements we set last semester, we're happy that we're able to demonstrate all of them today. These were performing trail path planning, operating autonomously, localizing itself in a GPS-denied environment, navigating the planned path, traversing uneven terrain, choosing the craters to groom and avoid, grading these craters, and validating them after manipulation. We also established a communication with user, which is the GUI that you see here. So moving on to our non-functional requirements, one was that the rover was way under 50 kgs. We met this easily. It's around 24 kgs. The cost for the project must be under $5,000. We barely met this one. We only have $5 left, hence there's no snacks today. But moving on, we had to get a computer that could run all required tasks. Since the rover is running, that was also met. Moving on to our non-functional requirements, these were some desirable ones that we wanted to meet. The first one was technological extensibility, so that the next team that comes will be able to build on top of our work. So we followed like good code commenting etiquette, and we have a very extensive wiki on our Notion page. So this requirement was met. One other was aesthetics. This was from Red, that the rover must look good while it functions. We verified it with him. He's happy with the way it looks, so we did achieve this. Another one was modularity. So the tool that is currently on only needs 3 screws to be able to be unmounted, and we can remount it with just as easily. So that was also met. And repeatability, we were able to achieve several test runs without maintenance. We'll also demonstrate this next week, so please do come back. And that was our presentation. Before we move to Q&A, I'd like to acknowledge some people without whom this project wouldn't have been possible. First is, of course, our project advisor, Professor Red, John and Demi, who have been our course advisors throughout this. Tim for helping us with all of the workshop stuff and always being there. Our team Creator Grader for being the predecessor to this project. We used their platform built off of it and also used a lot of their code as a base. Wenny for helping us with the laser scanner, Chuck for helping us with the total station, and Dr. David Wettergreen for letting us use this PRL. So thank you, everyone. We are Team Lunar ROADSTER, and that was our FED presentation. We open to any questions you guys have, please.
You guys have lots of different paths on the Rways. I think one is now missing. There were previously, I think, 3. Apart from the blue one, can you explain what are those?
So the blue one is the reference latitude. The multiple paths that you saw is actually the single path only, but as we mentioned earlier, that sometimes since we have penalized backward motion, so if it reaches here and the next goal, that is like they say the sync backplate, is behind the rover, then it tries to give it a circular path and goes around the whole thing. That's why you see multiple lines going around. That's usually why we see that kind of path being visualized, but that's not actually what the rover follows.
So this
is just one of the candidate paths.
Yeah. So basically, this is global nav. This publishes global nav planner. During that time, the manipulation planner is running, but the global nav is always running in the background. So it publishes this here, but we're not using it since the manipulation planner is what's going to actually command the motion at that point. Yeah.
Is a manipulation the orange or?
Sorry?
The manipulation planner on this, is it the orange or?
Yeah, it's all on board. There's nothing off board.
No, the color.
Oh,
yeah, the orange.
2, right? Like one is yellow, one is I think orange, and one is red.
Orange is what it's actually following. Like that is.
Yeah.
And but the manipulation planner are the poses that I showed earlier. The manipulation planner only outputs like 4 poses, these 4 poses, and that is what will be executed. But during this time, the global nav is still active, so that is what you're seeing there. On Zoom also.
Okay. So for the final round, you said that the rover would actually go over the craters it filled, but this one did not.
Did not. Yeah, that's nav error.
Okay.
We'll make sure it does next time. But the point is, it didn't have to avoid it, so it went as close as possible.
Right.
Yeah.
Yeah, it didn't avoid, but it didn't go over it either.
Yeah.
Oh, okay.
Does the onboard compute detect craters that might not have been identified from the previous planning? Like if there was an unexpected crater that was not in the map given to the rover?
We'll have to change state to the validation subsystem. If we need to trigger it. So if we are it will not trigger on its own because the Z is not always running. When it's in navigation, the Z camera isn't on. So we'll have to trigger the Z camera to turn on, and if it finds it, then it's going to manipulate it. Yeah, but that needs to be a trigger. It won't do it autonomously.
Okay, cool.
Yeah.
Okay, you said you were using YOLO. I don't remember what you said it was for. For crater detection?
Yeah.
Okay, can you talk about your data collection methodology and
we spent like a bunch of days just creating craters, and we made sure that all 5 of us do that so that we get a varied data set, not just like one specific type of crater. And we did that in different times of the day. So with sunlight, sometimes we got shadows and everything, so that our data is more augmented and robust. And we trained the YOLO V8 on that custom data set. We made sure that all the bounding boxes that we create are like within the size of the crater. That's why we see that when it's detected, we get the diameter very easily from the bounding boxes, and it also locates where the center is. That center detection is not part of the YOLO. That's done using the depth data from the Z camera.
So it's trained on the RGB plus depth? Like you get the RGBD from Z, but the actual training is on...
That is on just RGB data.
Yeah.
Okay.
Because we only use the YOLO for the detection of where the crater is. And then as soon as we get good enough stable detections, we switch to getting the depth data as well. That helps us calculate and determine where the centroid of the crater is.
Essentially, we get in camera frame where the crater is using YOLO, and then we use depth data and camera intrinsics to get it into the world frame. Yeah.
Do you lower the blade by a fixed amount?
Yes.
Yeah, currently it is a fixed amount. We wanted to do it based on depth, but it was just very varied based
Yeah.
on. So we have a certain tool height on the first pass and a lower tool height on the second pass.
Yeah.
And that seems to be fulfilling all of our criteria.
Given the types of craters
Yeah.
Yes.
and geometry. I guess you haven't done this, but have you thought about scaling, for future missions? Like if the robot were to be 3 times the size of this and the blade was twice the size, what types of craters, what would be the implications? I don't know if you had any chance to do that sort of thing.
Okay, so our performance requirements were kind of based on our geometry. So the 0.5 meter crater is based on, because our tool is 0.6 meters. So as long as you keep increasing the tool size, you can tackle more craters in this method that we use, the forward pass and the backward pass. But if you want to target the crater from multiple directions, you can do as big as the crater as you want.
And then, of course, you have to scale the actuation.
Yeah, all
and
of that will
everything
scale,
else.
yeah. With the weight,
We can
everything
add
is
yaw
on the scale.
motions and stuff like that to
Okay.
do fine trading.
You guys have strong ideas for Encore besides the Skycam, which I think you already planned.
That is the main idea, because that will
Cool.
screw everything up based on how our navigation system works, how our planner works, because the base of the localization is going to change. But yeah, we'll think of something else based on trying to show more.
Simplify the visualization.
Yeah. we were also thinking of putting more visualizations up, such as
Maybe a few big craters.
Yeah.
Maybe come up with a challenging layout.
Sure.
we
Like a
were
couple
planning
big
to do
craters.
that, but we barely have access to the moon this week,
Yeah.
Oh, okay.
considering. But we'll see how it works out. Yeah.
Will it be the same cost map next week?
We
also?
want to change it, but we don't have access to the moon for the next 3 days
Okay.
or 4 days. So that's the issue. We'll if we're able to do it, it'll be a different map. Yeah.
What aspects of the localization, like state, are you going to measure from the, like, what do you call it, Skycam?
Yeah,
Facing camera?
complete rover pose.
Okay.
Yeah, and then we'll fuse it with the IMU and the encoders, but
For the
it gives out a full 660 of using the Skycam.
You're going to use multiple lights for that, or
Yeah,
all of
all of
them?
them. All of them.
yeah, we have a
in a universe that has many suns, something like that?
No, this is Star Tracker.
Oh, it's a star. Okay,
It's a
I'm
Star
sorry.
Trek.
This is Star Trek.
Yeah.
A lot of bright stars. Yes. Good.
and we have a camera that can encompass all of this.
Encompass.
It's like a
Fish
fisheye camera that
Yeah.
looks at everything. We'll talk about it next week.
Okay,
Please do
next
come
week.
back.
Yeah.
Okay, thank
Awesome.
you.
Thank you.
Thank
Thank
so
you.
much.
When you graded the crater, the centerpiece was like quite flat, well within 5 degrees. The boundaries, which you basically